One of the most important equations in modern physics, if not the most important, is Schrödinger's wave equation. Just as Newton's laws describe how objects move in classical mechanics, Schrödinger's equation governs the behavior of quantum particles like electrons. But how did Schrödinger arrive at this groundbreaking equation? To understand that, we need to take a relatively short journey through physics history, where classical physics started breaking down, reality itself was questioned, and a handful of very confused but brilliant physicists desperately tried to make sense of it all. Our story begins in the late 1800s, when physicists were trying to understand how hot objects radiate energy. They had equations for this, Wieland's law, the Rayleigh-Jeans law, and others. But none of them quite worked. Specifically, according to classical physics, a heated object should emit infinite energy at short wavelengths, particularly in the ultraviolet range. This absurd prediction, known as the ultraviolet catastrophe, which, as an aside, sounds more like the title of a sci-fi B-movie, suggested that every warm object, including you, should be glowing with infinite energy. Since that is clearly not the case, unless you've been standing too close to Chernobyl, something was deeply wrong. Enter Max Planck. In 1900, Planck tackled this problem head-on. And by tackled, I mean he completely threw classical physics under the bus. Instead of treating energy as a continuous, flowing quantity, he proposed that it could only be emitted in discrete packets, which he called quanta. He introduced his now famous equation, E equals hf, where E is the energy, F is the frequency, and H is his own new fundamental constant, Planck's constant, which is a value of 6.626 times 10 to the negative 34 joule seconds. An incredibly small number, but one that would go on to reshape physics itself. With this new postulate, he managed to finally solve the ultraviolet catastrophe once and for all, with his newfound radiation law, in its rather ghastly form. Planck, however, didn't think of this as a grand new theory. In fact, he called it eine Verzweiflungstat, an act of desperation, because in his mind, he was just using mathematical trickery to make the equations fit experimental data. He had no idea he had just opened the door to quantum mechanics. A few years later, in 1905, a young patent clerk named Albert Einstein took Planck's idea and ran with it, right off a cliff as far as classical physics was concerned. While studying the photoelectric effect, Einstein proposed something even bolder. Light isn't just a wave, it's fundamentally made up of discrete particles, which we now call photons. This was deeply upsetting to a lot of physicists. For decades, everyone had just gotten comfortable with the idea that light was a wave, thanks to Maxwell's equations. And now Einstein was saying, actually, it's also a particle. Deal with it. Many physicists, including Planck himself, weren't convinced, but the evidence was undeniable. Einstein's photon hypothesis perfectly explained why light could eject electrons from metal surfaces, a phenomenon that classical physics had utterly failed to describe using the concept that light is a wave. But if light could behave as both a wave and a particle, that raised an even bigger question. Could matter do the same thing? Now, I know you probably have an image of the atom in your head, maybe something like a little solar system with electrons orbiting a nucleus like planets around the sun. That's because, for a while, physicists actually thought that was how atoms worked. But getting to that model was a mess. First, there was J.J. Thomson's 1987 plum pudding model, which imagined the atom as a positively charged blob with negatively charged electrons embedded inside, like raisins in a pudding. This made sense at the time because electrons had just been discovered and nobody knew about the nucleus yet. Then along came Ernest Rutherford in 1911, who after bombarding a thin gold foil with alpha particles, made a shocking discovery. Instead of passing straight through, some particles bounced off at extreme angles, like they had hit something incredibly dense and tiny. This led Rutherford to propose that atoms are mostly empty space, with a tiny, positively charged nucleus at the center. Great! Except for one enormous problem. Classical physics said that electrons moving in circles around the nucleus should constantly radiate energy, quickly spiraling into the nucleus and dooming all atoms to instant collapse. Since that clearly wasn't happening, something was very wrong with our understanding of atomic structure. Enter Niels Bohr, a Danish physicist who in 1913 proposed a radical solution to the atomic disaster. 1. Electrons don't spiral into the nucleus because they're only allowed to occupy specific fixed orbits. No in-between nonsense. 2. Each orbit corresponds to a specific energy level, and electrons can only move between these levels by absorbing or emitting energy in discrete packets or quanta. Bohr wasn't just making this up. His model actually explained the mysterious spectral lines of hydrogen, which had baffled physicists for years. He even came up with a simple equation for the allowed energy levels. En equals negative 13.6 electron volts over n squared, where n is an integer representing the energy level. This worked beautifully for hydrogen. The problem? It didn't work for any other atom. Whoops. Turns out the real world is a bit messier than a single electron system. It would take a wave equation to fully explain atomic structure. At this point, physics was getting weird. Enter Louis de Broglie, who in 1924 had a simple yet insane idea. If light can act like both a wave and a particle, why not electrons? He suggested that electrons had a wavelength given by lambda equals h over p, where p is momentum. This explained why Bohr's orbits were quantized. Electrons could only occupy orbits where their wavelength fit perfectly around the nucleus. This was a huge breakthrough, but it raised another problem. If electrons are waves, what equation describes them? Waves obey wave equations. Maxwell's equations describe light waves, for example. But what about matter waves? This is where Erwin Schrodinger enters the story. Inspired by de Broglie's matter waves, he set out to find a mathematical equation that describes how these waves evolve over time. After some brutal math, which I'll make a video on when I stop procrastinating, he arrived at what is now known as Schrodinger's wave equation, which, as you can see on screen, has quite a lot of forms. But essentially, psi represents the wave function, which encodes all possible information about a quantum system. Unlike Newton's equations, which predict exact positions and velocities, Schrodinger's equation only gives probabilities. At the fundamental level, nature is inherently uncertain and indeterministic. This idea horrifies many physicists, especially of the older generation who were quite fond of the idea that the universe was completely deterministic, especially Einstein, who famously protested, Gott verfällt nicht. God does not play dice. Bohr, however, just shrugged and said, Herr Einstein, hören Sie auf, Gott zu sagen, was tun soll. Einstein, stop telling God what to do. At this point, quantum mechanics was getting deeply weird. The wave function psi in Schrodinger's equation didn't describe a single definite outcome, but a superposition of all possible outcomes until an observation is made. This led to an unsettling question. Does reality only decide on an outcome when we look at it? To illustrate how bizarre this is, Schrödinger proposed his now famous cat experiment in 1935. Imagine putting a cat in a box with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. The setup worked like this. If the atom decays, a quantum event that happens randomly, the Geiger counter detects it, triggers the hammer, breaks the vial, and the cat dies. If the atom doesn't decay, the cat remains alive. According to quantum mechanics, before you open the box, the atom is in a superposition of both decayed and not decayed states. Since the cat's fate depends on the atom, the cat itself must also be in a superposition of both alive and dead at the same time. It's only when you open the box that the superposition collapses into one definite reality, cat alive or cat dead. Schrödinger wasn't actually suggesting that cats exist in some zombie-like half-alive, half-dead state. He was mocking the idea, showing how absurd quantum mechanics seems when applied to everyday objects. And yet, experiments have since confirmed that superposition is very real. Just much easier to observe with particles than with cats. For now. And that brings us to today, where this equation remains one of the most important tools in physics, shaping everything from modern electronics to our understanding of the universe. And thus, dear viewer, we arrive at the end of our little foray into the history of Schrödinger's wave equation, a tale of mathematical triumph, shattered classical illusions, and deeply disgruntled physicists shaking their fists at the heavens. Now, if you found this enlightening, or at the very least, mildly entertaining, perhaps you'd consider liking, commenting, and subscribing, so that you'll always be notified whenever I release my latest mad ramblings. Incidentally, I am currently working on a longer, more in-depth video that explores all these ideas in greater detail. When will it be released? That depends entirely on when I triumph over my greatest adversary, procrastination. So, stay tuned at some indeterminate point in the future. Until then, remember, the universe may be probabilistic, but your choice to engage with this channel need not be. Ich wünsche Ihnen einen guten Tag und Gott sei mit Ihnen.